Hi everyone, and thanks for your time today and joining us for this webinar titled The First Steps Towards Electrical Fire Prevention in Buildings through Arc Fault Protection. That was a mouthful, so let's get straight into it with the agenda for today. So let's look at the topics that we'll be covering during this webinar. We will firstly look at the market drivers and how the standards have changed to meet this requirement around arc fault detection. We'll then deep dive into the topic of arc faults and understand better the technology that is available to help prevent fire prevention in specific installations. And then we'll finish off the webinar with a Q&A session at the end. But before we get started, I just want to go through some housekeeping and just make sure that everyone understands what's available to us. So all attendees will be in listen-only mode. As I mentioned, we will have time for questions and answers at the end of this webinar. So you can use the Q&A icon that is located at the bottom of the browser to send us any questions during the session. If you do need any technical help, please do use the help icon indicated by the question mark that's also located at the bottom of the browser. You can also use the F5 button to refresh your screen if the webinar slides do not appear to be advancing. I'd like to now introduce our speakers for the session. Firstly, myself, I'm Ras Jayakrama, Channel Manager at Schneider Electric, and I will be the moderator for today as well. So I've been in the building services industry for more than 15 years with a Bachelor of Engineering degree. And one of my current focus is the consulting group and how we can support businesses through education as well as innovative technologies to, I guess, help meet the changing market needs, especially in the digital world. The first presenter today will be Gary Busbridge, our Standardization Manager at Schneider Electric. So Gary has been in Clipsal as well, now Schneider Electric, for over 43 years after graduating from the University of South Australia in 1973. So his role of Standardization Manager is to ensure global as well as national standards are aligned to the electrical contracting business and the electrical accessories manufacturers. This also includes the relevant IEC standards and applications. In November 2011, he was made chairman of the EL001 Wine Rules Standards Committee. Our second presenter for today is Justin Barrett, Offer Manager for our final distribution range of products and solutions. So Justin has been in the electrical industry for 20 years and has been part of the Schneider Electric team since 2006. As a graduate from the University of Wollongong with the Bachelor of Engineering, his experience has been focused on low-voltage electrical distribution systems, and he's also on the Australian Standards Committee EL-004-09 for RCDs. So let's get straight into it. I'll now hand you over to Gary to take us through the first part of this webinar. Over to you, Gary. Thanks.
Hi. Thanks, Raz. Glad I can be of some assistance in this story about the arc fault detection device. What I would like to do is start off with a bit of the history of the standards adoption globally. It actually did start in the USA. It was called, what still is in the US, an arc fault circuit interrupter. So AFCI is their acronym. As you can imagine, the USA are governed by UL or the laboratories in regard to their product standards, and they're predominantly about fire protection. So they are most active, and as you can see by the time line that I've provided there on the screen, they started work back in the late 80s early 90s about what an arc fault circuit could do. They eventually introduced into their national wiring rules in 1999, and it's gone on from there. Now it is mandatory for residential bedrooms and socket outlets within the installation. The I saw this as a good opportunity and decided to do some initial development of their own in 2008. However, they did actually change the acronym to an AFDD, the reason being to follow the principles of an ELCB or an RCD. Now we have an arc fault detection device just to follow in the same context as a residual current device or earth leakage circuit breaker. The AFDD was released to the market in 2013 to Europe after the standard was published. So there is a standard that IEC 62606 that we here in Australia would follow as we've now moved into that. In New Zealand, the AFDD was released in 2016. So New Zealand people on the line probably have some experience with the AFDD. In Australia, for the most part of the revision of the 2007 edition of the wiring rules, the AFDD was included as an accepted safety protection device. So there was much discussion at the committee about where that should go. Eventually, it's been put into its own section in regard to the prevention of fire. So now it is incorporated. So it was put into the 2018 edition, which came into being on the 1st of January 2019. And it's only a recommendation from an Australian perspective. And you would consider the usage for bedrooms or living areas, museums, places where you would be storing very expensive and rare articles, wooden structures. So in Australia, I think from a home perspective, you're talking about the big Queenslanders. I mean, they're all timber. If they get any sort of fire in there, you've got a real problem. So the AFDD, which includes the RCBO into that device, that's being released to the market shortly from a Schneider perspective. So we will have a product in the market. It's important to understand that in New Zealand, AFDD installation will be mandatory when they cite in their government Gazette the 2018 version of the wiring rules. They aren't quite there yet, but when they do, it will be mandatory to use the AFDD, as you can see there on the screen, for the storage of flammable materials, storage of irreplaceable items, historic buildings, socket outlets in school dormitories. So they've gone one step further than us in Australia. What is an AFDD? The next slide is to try and give you a bit of an overview of how these units work. Essentially, they detect an arc fault in damaged TPS, flexible cord, so cord extension sets, or maybe even poor termination at the back of a socket outlet or whatever in a circuit. And these are applied to only one circuit, one final sub-circuit. They don't get used to cover a whole installation. You need an AFDD to each circuit. The arc faults are small of nature, and Justin will explain that a bit later. And they're usually a series or a parallel fault across broken or severed cable. And it's a very small arc that's created. But eventually, if it continues, it does actually carbonise the plastic installation material of the cord or the cable. Got the right conditions, eventually that will create a fire The terrible part about that is that while it is arcing, it's smoking. When you're asleep, you don't smell anything. So you have a problem detecting that. RCDs were originally marketed as a means to detect a fire and cut power. That was one of their, other than the personal protection they provide. But they're pretty hit and miss in that regard, because if it's an active neutral issue, they won't trip out. It'll only be an overload situation. So it may or may not detect the fire. Heating alone, to detect heat in the early stages of the fire process, and really that's a warning only. Smoke alarms themselves are only installed to detect smoke in the next stages of the fire process. And again, that's only a warning. The early steps may be to use a fire extinguisher to tackle the initial fire source, if you're lucky enough to get to it early. By this stage, the fire may have taken a strong hold, and the best option is to get out using your exit signage to get it out of the place. Basically, the result is devastating. You've loss of property, and worse still, loss of life, which is something we read about quite a bit in the papers. With an AFDD installed after the MCB, RCD, and on a final subcircuit, the instant that the arc fault is created, effectively the power is cut off to that circuit. So the opportunity for the fire to actually generate is cut there and then. So hence I've got a before AFDD situation where the electrical current continues, or with ED, you basically cut off that electrical fault at the very early stages. So minimal damage and maybe no damage at the end of the day, other than to the cord set. If we look at fires themselves, and this is one of the reasons why we at the wiring rules had to consider where we go with AFDDs. And if you look at the graph, there's a lot of information on there. But the nature of a fire is that it actually has a very steep curve. And as you can see from the time scale on the bottom, we're talking about 3 to 5 minutes for a fire to take hold to full development. So it isn't much time. And the interesting part that 30 years ago, we were talking 15 to 17 minutes to get out of the place before the fire took hold. And that's predominantly due to the design and construction of buildings nowadays. There's more open plan, maybe higher ceiling, the ability for the fire to move through the whole place. Also due to the plastics in equipment and furniture. We've got plastics in everything now, carpets, curtains, whatever. The toxicity and the amount of smoke has increased to over 200% from what it was 30 years ago. The chemical composition of the fire has greatly increased the speed at which a fire can actually take hold. So you've effectively got 3 to 5 minutes to escape. There is a bit of an explanation about how the fire goes there and how it grows. But certainly once it gets to development within that 3 to 5 minutes, then there is a decay, which is actually where it's actually burning itself out. But this is when the fire's taken great hold and effectively the most damage has happened, and the structure or equipment within is actually burnt pretty badly. So if you have a look at the AFDD, you're talking about at the initial stage, as soon as there's an electrical fault. Okay, the AFDD is not going to do much for you for if it is just a normal fire that starts. But if it's an electrical fire that is the cause, and we have seen a lot of statistics to say that it does start with electrical fault. It basically cuts off within that minute So you're actually killing the source of the fire right at the start. And just to finish off, I mean, it's a opportunity, it's improved safety. If you look at where we have been over the years, is a sort of an opportunity, it improves safety. We started off with fuses many years ago. But they were slow acting and they were only property protection at best. MCBs came onto the market, took hold, replaced those fuses. They provide an overcurrent protection. They certainly increased the reaction, speed of reaction to the overload. But again, they're property protection in the main. RCDs provide that earth leakage protection. Active or neutral is touched while you're in contact with earth and trips out pretty quickly. They can be property protection. Obviously, you've got 300 milliamp and 100 milliamp versions. But in the main, they're about person protection. They're about personal protection. We've seen that actually the decline of electrocutions has been immense over the last 20 years. Surge protection devices, they were the next one, or they've been around for quite a while, but they provide protection from overvoltage scenarios, lightning strikes and the like. They're aimed at instant and equipment protection in the main. And now we've stepped out and we've rounded out with our protective device suite with the arc fault detection device. These provide property protection in the main, but provide a safe scenario for persons within that property. So it's a device. Over time, these devices will prove their worth to the market. I think as we get more and more used to it, eventually it'll be a necessary addition to all installations. So I would say that the way the wiring rules progresses, that eventually it may also be treated within Australia, but it certainly needs the proof within the market here. And that is my presentation. Thank you very much. I'll pass back to Raz.
All right, thanks, Gary. It's good to, I guess, see that, get that insight, and also, see how that the industry is moving in the right direction to, ensure that we have better safety in the places that people reside. I guess for Australians, we've seen firsthand, how fire can really impact people's lives. So, yeah. I'd like to hand over to Justin Barrett for the second part of the webinar. But before I do that, just a friendly reminder that at any time you're welcome to start posting questions by using the Q&A icon that is located at the bottom of the browser. With that, I'll hand over to Justin. Thank you.
Thank you, Raz. Thank you, Gary. Okay, so I'll be focusing more on the product and the technology itself. So you just had a background on how the standards have evolved and how we've progressed from fuses through SPDs through to RCDs and now AFDD. But just to give some examples of why what causes arc faults, it's more to do with aging installations. Some of the examples are loose wall sockets, older cables, or poor connections. So for any of you that have seen any incidents reports within the industry, you keep them in mind. You always see these examples of product or cable that's got either some arc or some carbonisation around it or excessive heat. The other one is misuse. So a more common situation within our homes and within the office environment is the examples where we've got power supplies for our laptops where the cable's been pulled too many times and sticking out the back of the transformer. Office chairs rolling over extension leads that are sitting on the floors within our office. So that type of misuse, so we obviously have test and tagging in place within the industry. That's intended to capture a lot of that, but there's many examples of cables that are still used and abused and not rectified at appropriate time. And then aggressive environments. So we've got situations where cables might be exposed to external environments, whether it's UV, temperature, enclosed environments, and also with vermin. So we've had a number of incidents where rats, etc., have chewed through some of the insulation, and over time that has caused an arc fault situation. So just demonstrate that more clearly, what's on the screen is a typical extension lead with the active and neutral through it. So the fault is generated through erratic paths. So the current, as the insulation between those conductors has deteriorated, you have small currents arcing across. That's generating enough heat in a very local situation to the point that the heat with these smaller arcs can be getting up to 5,000 degrees. Because it's so small and such a small amount of energy, it's not creating a fire in itself. But this cycle of erratic arcs continues on, and over time that carbon becomes more substantial. And there's two places where that can occur. That is just physical damage to the insulation itself due to contact pressure or wear and tear, or the other one is through excessive bending of the internal conductors, and you start having breaks in the individual strands of the conductors internally. So you end up with this cycle where you have a small arc, creates a bit of carbon, the current path can more easily pass through that carbon, creates more arc, creates more carbon, and you have this repeating cycle that continues on until a certain point you've got enough heat which then creates the ignition into flame. So to demonstrate that more clearly, this is a little test setup demonstration that we did. What you can see is an MCB going through a supply and a cable. The cable has some internal conductors that have been damaged, so the individual strands are damaged inside the red cable, and it's connected to a simple fan heater. So at this stage, the MCB is in the on position, the fan is in the off position, and then when we turn this fan heater on to its first setting of just 1,000 watts, some smoke started appearing from the cable immediately. That smoke, if this cable was in the wall, would not be visible for a long period of time, and in that situation smoke detectors would not pick it up. This test went on until that carbon situation resulted in a flame, and in this case the actual flame started in less than 5 seconds. So keeping that in mind, it was only 1,000 watts on this particular load, and yet with the damaged cable we were able to create a fire in less than 5 seconds. No AFDD was installed on this circuit, therefore it didn't trip. So I'll be explaining shortly why the MCB did not trip in this case. So we've got the existing protection of MCBs, RCDs and surge arresters, and even overvoltage detectors. None of those will detect that type of arc. The reason is that it's small in current and small in duration in time, and usually there's two types of arcs. There's a series and a parallel. So from a standards perspective, there's been a lot of testing done to determine how much current and how much time is required to get to ignition point to create flame. And that standard is referred to as 62606. And the most common example that we like to highlight is that it only takes 2.5 amps and 1 second for ignition of a flame. So on this curve you can see the blue curve for series arcs. What it's indicating is the tripping curve for an AFD device. We must trip before we get to that curve. So as you can see, as the current gets higher, the maximum breaking time or tripping time has to reduce to allow for the same amount of energy. So at 2.5 amps must trip in 1 second, and at 63 amps it must trip in 0.12 seconds. MCBs won't see that because they can't trip that fast enough, and if it's in series, the MCB just thinks that it's part of the load. It doesn't see any difference. And an RCD won't see it because, again, if it's in series or it's just going from active to neutral, there's no loss of current to an earth anywhere, and therefore it's still balanced internally on the RCD and it won't trip. So parallel arcs, we get up into the higher current. So the second table there for parallel arc faults, at 75 amps, we have to trip in less than 12 half cycles. A lot of people would think that with a parallel arc, the MCB will trip, and it will once it gets up into the higher currents. But if you think about a common light and power circuit, and it's got a 16 amp MCB on it, it won't trip if the arc fault is at 75 amps because it is below that tripping threshold. So to demonstrate that more clearly, what we've got in this graph is the typical tripping curves of a breaker, so your B, C and D, and overlaid on that same graph is the tripping curves in the blue for the series arc and the tripping curve in orange for the parallel arc for what the standard state AFDD must trip in. And as you can see, both of those curves are substantially below the tripping curve of MCBs. So how is this done? What's unique? What's different with an AFDD? It's all about the detection technology inside the device. So it's doing a real-time analysis of the electrical signal. So we're all used to the typical AC sine wave shown in the green before arcing. And AFDDs constantly monitor that sine wave. And what they're looking for is anomalies in that sine wave. So when an arc does occur, that sine wave becomes non-standard and there is noise. So it's looking for things that are greater than 2.5 amps because that can cause a fire, a duration of more than a second because that's the threshold at which a fire can start. So that's a exclusion topic for minimising nuisance tripping as well. So there's a fine line. It's quite easy to detect differences in your AC sine wave. The more challenging part from a technology perspective is ensuring continuity of service and minimising nuisance tripping. Such things as we have arcs coming from electric motors, we have other high frequency disturbances through other switching actions. These type of things are taken into account with the analysis and the decision process. So going into some more detail on that, the example of electric motors. We're used to seeing different arcs occurring inside rotating motors. Because that's relatively repetitive as the motor's constantly turning, we can allow for that. So we're looking for things that are repetitive and excluding that. If it's not repetitive and erratic, it comes back to those erratic arcs that I referred to earlier, where that inconsistency is a reference point to say that some sort of arc fault is occurring on that circuit. Also, whenever an arc is established, it changes the frequency on that circuit as well. So we're monitoring what frequency and what variations there are happening to the frequency on that circuit. This is an internal view of the device. So most of you would be used to an RCD. With an RCD, it's just got a toroid around the active and neutral, and it's just looking for the imbalance. As long as the current going through the active equals the return current going through the neutral, everything's balanced and it doesn't trip. That is also in the all-in-one device. So what we're showing here is a AFDD device that has MCB protection, RCD protection, as well as AFD detection. And you can see that there's a current sensor for the incoming active, there's a current sensor or toroid for the RCD part for both the active and neutral, and then there's also voltage measurement. We're constantly measuring multiple parameters, and there was an animation on that slide that's not working, so I'll just have to talk through it. So you can see that the measurements that we're doing are current, voltage, and we take that signal, we process it digitally, We're looking for any variations in the types of waves that are there, and then there's an algorithm within the device that makes a decision on whether the product should trip or not. As mentioned before, the biggest challenge for this technology and a bit of delay from the IEC adoption of it was to ensure the continuity of service and not tripping due to other known sources that would create interference on the sine wave, but not a safety issue. So there's two main types of arc faults that can contribute to fire. The first one is in series. So that's simply within the same conductor itself. And the other one is in arc, so in parallel. So when an arc happens to jump across from the active to neutral. We have the capability to detect both of those. It's just the difference in the threshold of what current we would actually be detecting for each of those types of arcs. So moving on to the comparison of what we're doing currently and how AFDD can be installed. If we've already got an existing installation with an existing RCBO, so on the screen is the most common RCBO that we have within the marketplace, so combined MCB plus RCD. And the simplest way to add AFD to an existing circuit is through an AFD-only device. So this particular device has the AFDD detection in it, but does not do RCD or MCB because it's assumed it's already provided in another device, and you simply put this in series with it. However, the simplest way for a new installation is to go straight to the all-in-one unit. So the all-in-one unit has MCB, RCD and AFDD. It can be used and designed up front. The most important thing from an installation and design point of view for me to mention though is that this is a 2-module wide or a 2-pole wide device. So it does have some implication on your installations and designs, but it's not practical with current components and current technology to be able to get this type of all-in-one technology into an 18mm wide device. As you can imagine, RCDs are already jammed packed with lots of components to do the MCB and the RCD, and we've come along and put extra components in there for the AFDD section. So we've had to go with this form factor and this format. It is targeted for single-phase circuits, and 6, 10, 16, 20 and 25 amp is what it's available in, and the people protection RCD setting is at 30 milliamps. So as we have a whole heap of scenarios that could cause this product to trip, there's a lot of options regarding the indication on this to give feedback and help with maintenance and diagnosis as a result of any tripping that may occur. So with this device, there's 2 toggles on it. The left-hand toggle is for MCB and the right-hand toggle is for the RCD. So straight away you've got an indication on if it turned off due to MCB, so overload or short circuit, or if it turned off due to earth leakage. If it was earth leakage, both handles would be off. If it was just MCB, then just the left-hand handle would be off. We also have some trip windows on there as well, so there's red flags above both of those toggles that clearly indicate it was a trip and not just someone manually turning the product off. So this is clear indication on the front of the device whether the product was turned off or whether there was an external influence that caused it to trip. In addition to this, when we move into the AFD part, we've got LED status indication. So there's diagnostics if there was a trip. We have a test button on this product that allows you to test the mechanics of it. You press the test button and the device will go to the off position. But we can also, through a sequence of pressing that test button, get feedback through an LED status indication on what the fault was if it was on the AFD section. So with the LED, we can indicate if it was a series arc, a parallel arc, if it was an arc to earth, or if it was an overvoltage, or if we've got some internal error within the internal components and the algorithm itself. So just as a recap, current protection devices that are in the market cannot detect series arcs or parallel arcs that can contribute to the ignition of fires, and the only devices that can do that are those that have the arc fault detection technology built in. And there's two options there. You can buy a standalone device of just arc fault detection to complement existing MCBs and RCDs, or you can buy an all-in-one device that has the MCB, RCD and arc fault all-in-one. So that was a brief overview of the technology and the products available. I'm going to hand it back over to Raz for the Q&A.
All right, thanks, Justin, for that. And it's great to see, I guess, how technology has playing its part in helping to prevent, fires in these types of buildings. And I guess, from your presentation, it's obvious why arc fault detection is more of a focus in our standards and the importance of considering such solutions for those required applications. All right, so we're coming to an end on the presentation part of the webinar. So you're still welcome to keep posting questions using the Q&A icon at the bottom of the browser. And we should have time to go through those questions with our experts on this webinar. But before we get to the Q&A, I just want to do a quick overview of how when designing and or implementing a solution across your main switchboards right down to final distribution, there are different, I guess, offers and technologies that can be considered to ensure a better approach in electrical fire prevention, especially for those specific building applications that we went through. We can start off from, continuous thermal monitoring, as well as power connection accessories in your main switchboards, to technology such as buzz duct trunking systems and RCD protection on your distribution circuits, to, what we talked about, today, with regards to arc fault detection, for your final distribution. And I guess something to highlight that these technologies are now connectable, in one form or another. So that's given us better visibility, through software integration into these applications, so that helps us manage those preventative actions, but also in the event of a fault, allowing personnel to address them as soon as possible. So we'll keep you posted as we have a few more webinars that are coming up that will continue this focus on electrical safety. So let's have a look at the key takeaways from today's session. So firstly, we've seen how the local standards of AS NZS 3000, recommends the use of arc fault detection device technology, especially on those specific applications, where safety of people is critical. Secondly, it's been demonstrated, how devices with arc fault detection functions can help with the protection against arc fault, for example, using an arc fault detection device. And thirdly, electrical safety with regards to fire prevention comes in different forms across the entire electrical network. So now I guess we'll like to take a look at some questions, and hopefully we'll get through all of the questions. But in the instance, if we can't get through all of them, we will record the answers and we will email those answers to you. All right, so let's quickly have a look at the first question here. So not in any particular order, but I guess this question is probably more for Gary, but Justin, you're welcome to also jump in. But do you see AFDDs becoming compulsory in the future through AS? Okay.
I think that's a matter of time. The market in Australia is definitely not even in a learning mode at the moment. But as these come into play, we'll get more and more evidence in regard to fire and the reasons behind fires that will actually lead to perhaps a downturn in those. And as that does occur, certainly the regulators, the insurance industry will probably put pressure on our standards to actually adapt and perhaps go to a mandatory. I can't see it happening short term, but certainly down the track as we get more evidence.
All right, thanks, Gary. All right, a second question, I guess for Justin. How will the operation of the AFDD work with the operation of a welding equipment, for example?
Yep, so recommendation from manufacturers of AFDD is that examples of things like welding equipment could cause nuisance tripping. We can't avoid that. We're monitoring that sine wave all the time. My recommendation would be to exclude those circuits at the moment. We are constantly evolving the technology and tracing all the type of known loads. Things like washing machines, a lot of the smart drive washing machines, they were causing a lot of the biggest issues when AFDD technology was first being developed. For now, I'd treat as high-risk loads, if I class it as that, the welding equipment, not to put the AFD on it because there's a high chance that it would cause some nuisance tripping, only because of the erratic stop-start that you'd have in a welding situation.
All right. I guess another question for you, Justin. Has your AFDs always had RCD protection built in, or were the earlier ones on MCB AFD?
So earlier ones were a switch only for isolation with AFDD detection only. So we have not launched or commercialised any AFDD in Australia with MCB or RCD protection in.
Just a question here. Are there plans to change the DB chassis to easily accommodate AFDD across each phase?
Yes, so for those who know the chassis as well, 18mm pitch is the most common chassis that we have. If you picked it up in the presentation, these products have the terminal screws at 9mm apart. There is an existing chassis. It is only in the coated style chassis that is available right now. We're looking at developing a encapsulated version of that to allow AFDD to be installed on a chassis. So yeah, keep that in mind. There's definitely a chassis available right now. And as we go through the better acceptance of AFDD, we would put some standard distribution boards into the marketplace that would allow you to directly fit it. At the moment, we can manage any of that either as a loose chassis or as a special DB.
All right, and there are a few questions, I guess, around cost. So, you know, what is the cost of a AFDD?
Yep. So it is mainly focused on, well, we only do single phase. It is brand new technology. We don't have anywhere near the volumes in manufacturing of this product as what we do with existing RCBOs. So yes, it's a valid question, and don't expect it to be anywhere near the same price. So typically you'd be looking at 4 times the price going from an RCBO to a AFDD device. From a standards point of view, that is recognised because it's difficult to justify doing it on 100% of circuits. So you can do your risk analysis on which circuits you would apply it to. So if you had a full building that was completely like a museum and it was all high valued, rare equipment, your risk profile is going to be very different compared to a commercial office building. But then it's coming back to what your combustible materials are within that building, and if you've got storerooms and that type of thing. So as we're evolving within the marketplace and it's being adopted into the marketplace, we would expect those more high-risk buildings, high-risk locations being the target for AFDD.
All right. What would be the recommendation for emergency circuits, such as, you know, lighting, emergency lighting, exit signs? Is it combination or what's?
Yep. So for me, emergency lighting circuits would be excluded because they're critical for the evacuation of the building. So you would not be putting AFDD on that. The only exception to that is if it was supplied by cables that were going through highly combustible petitions highly combustible, or even some of the old buildings where there's a risk of the deteriorated cables. As a personal example for myself, my brother-in-law's parents living in Auckland in New Zealand, they had a house fire last year. The actual cause of that house fire was they were going through a renovation of the house. An electrician came in, crawled through the roof space, disturbed a few cables, and that evening they had an electrical fault in the ceiling and the house burnt down. It was contributed to the electrician actually applying some pressure whilst they were crawling around the confined space, damaged the conductors and the insulation, and there could have been some tragic consequences of that. So that's another very quick, simple example. If there's some known issues on the wiring, then you'd be looking at installing AFDD.
I guess, with the AFDD and with any type of device, there's always testing required. So what are the testing requirements for such a device?
Yep, so same as RCDs, same practice. You would have noticed there is a test button on the front face. Test intervals through the test button. You would still be expected to do your normal RCD 30 milliamp testing on the all-in-one device. Other than that, there's no special test equipment for testing just the AFDD. We do that through the test button itself.
And I guess, what is required after the AFDD has tripped? I mean, what can be done?
Yep. So the instruction sheets that come with the product go through a range of diagnosis. So the very simple one up front is for reviewing what the LED status indication is on the device, and that will give an indication of what caused the trip, and that narrows it down to what maintenance work would have to be done afterwards. If it's a regular thing, and it's because there is a chance that it's just a one-off event, if it has happened a couple of times, then there are more detailed ways where we can actually download the trace recordings from these devices and actually look at what was causing that tripping. That's all detailed within the instruction sheets that come with the product.
I think you may have covered this one, but we'll just recap on this. Does an AFDD have overload protection, or must it be coupled with an MCB?
Yep, so the all-in-one device definitely does have RCD and MCB in it for overload protection, but you can buy a AFD-only device that does not have. So there's essentially two different versions of AFD, one with MCB and RCD integrated and one without.
All right. Can you use one device to protect the whole house?
Your limitation is that the highest current rating we go to is 25 amps. So the short answer is no, because there's not going to be enough supply for your house. And it comes back to the recommendations of RCDs. So RCDs, we expect the loads to be split across multiple RCDs for the reason of continuity of service. You don't want to have a device that's the primary supply for the house turning off and not having any other secondary power or lights available within that building. So the recommendation would be very similar to RCDs, where you split the loads across multiple devices.
All right. How do these non-standard ARCs compare with switch mode power supplies and the infinite permutations therein?
So with switch mode power supplies, a lot more of the noise is at the higher harmonics, so that's relatively well known. So from a technology point of view, as Gary mentioned at the start, the technology's been around for many years. And from a switch mode power supply, there's still some cycles or repetitive signals there that we intentionally exclude because we know what it is.
So can AFDDs be used on equipment that are connected to variable speed drives?
Similar thing for me, for a point of view that it's only single phase up to 25 amp. My recommendation is that it's not required for VSDs. Same thing, we all know that it's very difficult. So My simple comment to that when you're making the decision is if you've got an RCD on that circuit, then AFDD would behave similarly, but you'd have a little bit more risk of it tripping. And then it really comes down to the decision of how important it is for that load to remain on compared to the extra safety that you'd have from having the AFDD installed.
All right.
Could I just jump in there, Raz? From what Justin's saying is correct. If you actually look at the RCD applications now within wiring rules, there are many exceptions to having to use RCDs in both in commercial and industrial. But one of the key ones is about the fact you've got to look at the risk of nuisance tripping. And I would say that if this ever became a mandatory, then we would definitely have those exceptions based on the risk aspect. So, so that's basically what I thought I'd add to that story.
All right, thanks, Gary. All right, so does the trip LED, which shows what has caused the arc fault only, come on the combined RCBO unit? So does it only come on the combined RCBO?
The LED status indication is on both the standalone AFD, because the LED is only indicating what the AFDD detected. So it's on both.
All right. Question here, in the case of a parallel arc fault, just trying to understand this question, would the fault finding results with IRT change or still be 1 megaohm by the time this device is operated? Is that question clear?
Yeah, I'm not sure the intent of that question, so I'll have to take
that
one and come back
with an answer on that one. We'll follow up on that separately. Question here, can AFDD have 3 MCBs downstream like a 63 amp RCD?
We're limited to 25 amps, so I can see the intent of that. It's still common practice to do a 63 amp RCCB with 3 MCBs downstream of it. I don't see much advantage in that because with the limitation of 25 amps, unfortunately.
Are there any AFDDs for arc detection on submain circuits?
Not at this stage. Stay tuned. So once again, it's just single phase, 25 amp. The primary expectation here is that we're at the final sub-circuits. We're talking about all the sub-circuits where there's the smallest cables, the ones that are most likely to be damaged, most likely to be exposed to wear and tear, and in a portable environment where we're interacting with those cables.
Yeah. So I guess it kind of answers the other question here. Is there any device for high current applications for greater than 100 amps? So at this stage,
no. So nothing greater than the 25 amp. We start moving into different technology when we're needing to go higher than the 25 amp.
Will the AFDD detect faults within a unit? So, for example, air conditioning. Largely there's some house fires that may be due to air conditioning in the roof.
So the all-in-one, in my view, would, because it's got the MCB, RCD, and AFD. So if there was an electrical fault within the air conditioning, so assuming it wasn't just purely heat and it was something to do with heat exchangers, if it was an electrical fault that caused the fire, then all of those scenarios are covered by the all-in-one device.
Just a question on the voltage. So what's the maximum level of the nominal voltage for these AFDDs?
So it is actually designed to detect overvoltage for a long period of time. So your surge protection is just looking at transient overvoltage in the microseconds. AFDD has, because we are monitoring the voltage, we'll actually trip if there's been an overvoltage for a sustained period of time. I'd have to look at the data on that, but it's in the vicinity of a few seconds. But it's set for detecting it from 275 volts. I hope that answers the question as far as what it can withstand. So after that, it will detect it and actually trip and protect itself.
And I guess, with trips and all that, is there a limit to the maximum number of trips before the device needs to be replaced?
So from an AFD perspective, the tripping is very low current. You saw before we were talking about 2.5 amps, so it can easily handle that. The replacement of the device would still come back to normal guidelines for the MCB section. So the devices that we have are capable of 10 kA protection. So if it was a short circuit or significant overload that the MCB section tripped, then normal rules would apply for replacing it. If it's purely just tripping due to the AFD, then for my view, the first one might have been a nuisance trip, but the second one means you've definitely got some issues on site, and you'd be looking at investigating that further and rectifying whatever the fault was that was causing it to trip.
A question here is, I guess, and your thoughts on this, is there any risk to medical devices in the home needed to, keep a person alive?
Yeah, so when it comes to medical devices, and if you're talking about dialysis machines and things like that, they have very strict exemptions for continuity of supply. And I might open that one up to Gary, because I know he'd have some further comments on that around 10 milliamp RCDs and medical equipment in the home.
I think to answer that is that what the AFDD, its intent is to monitor situations where you aren't actually looking for a problem. So with a damaged TPS or flexible cable, cord extension set, or poor termination. So it's something that you're not monitoring. I think in a medical situation, if you're talking about home, dialysis or whatever, you're actually physically monitoring that. You can see everything that's attached. In a medical installation, again, 10 milliamp is it's such a low earth leakage value that if you do have any problems, it will probably nuisance trip. The necessity for arc fault, maybe, but I don't think we've seen that evidence in fire statistics at the moment, that it is actually affecting those medical installations.
All right, thanks, Gary, for that. How is the device interrogated? Do we take it out, send it back to Schneider, or is it through Bluetooth, plug-in comms? How's it done?
Yep. So if it does get to the point of doing some detailed interrogation, there are capability where we would send someone from our field services team either out to the device, and we've got test jigs where we can actually plug into the side of the device and download a trace history of what's been happening on that site, or we can have the product returned back to us and we can do some further investigation. So that's if we're getting into detailed trace analysis of what's been causing it to trip. That's definitely done as a specialised equipment, a specialised jig. Just in addition to that, from just general remote reporting, we can put auxiliaries on the side of this product. So any of our Acti9 MCBs, RCDs have standard auxiliaries that go onto the side for remote indication. We can do that with AFDD as well. So that puts it back into your BMS. So if let's say you had 10 critical circuits within a building and you wanted to get some feedback back through a security desk at the front office of the building, you could do that quite simply through auxiliaries.
Has there been any history of nuisance tripping on these AFDD devices? In cases where there's no damage of cables or switches?
So definitely during development, there was many examples of that. So the electronics sensitivity of it, the algorithms, the tracing, all of that comes together to make the final decision on whether it should trip or not. Part of the launch within each country is we do extensive field testing for that particular country and the network and the variances. So some of the things that are unique for us in Australia is some of the control signals that we have for the utilities controlling the contactors for off-peak hot water, for example. That's not experienced in other countries. We needed to allow for that and build that into our algorithms to ensure that it did not trip. So some examples during the start and during the development, but everything that's known to us now is built into it, and we don't have, the short answer is we've just gone through extensive field testing and we're very comfortable with the reliability of the product.
All right, just be mindful of time, so we'll just look at a few more, just probably 2 or 3 more, and then we'll start wrapping up. I guess a few questions around installation. So we talked about the chassis side of things, but with the typical installation of the AFDD.
So 2 views on that. If it's only a couple of circuits, then you just put on your auxiliary DIN rails and cable connect them. If you're looking at doing a complete board and it's 100% AFDD, then you'd have to use the dedicated chassis for the product, and that would be a special DB for us. As this product becomes more widely accepted and more widely adapted, we'll have more solutions to make it easily deployed.
I guess a question around solar. So what is the performance of AFDD devices solar system installations in your household?
So for me, the solar is all upstream of these devices, so it would have no direct impact. So DC solar panels going through the inverter, and all of these products are going to be on the AC side of the inverter. So as that's upstream, I would not expect AFDD to have any impact if there was solar or non-solar within that installation.
All right.
Just to add to that, Raz, there is work happening at an international level, OIC, to arc fault detection within photovoltaic systems. But it's only early days.
All right, good to know. Thanks, Gary. All right, so we've just gone over the hour, so I think we'll look at the remaining questions and get back to you on those. So I'd just like to now, I guess, take this opportunity to just conclude the webinar. So what's next? Please do keep a lookout for our next webinar. And if you're not receiving any communications around our webinars and upcoming webinars, please do get in touch with your local Schneider representative or myself. My contact details are on the webinar platform. This webinar will follow up with a survey at the end, so please do take some time to complete it and provide us your feedback. If you haven't noticed, there are some resources available on the webinar platform for you to download that will help support this topic. And this webinar will be available after the completion to have a look at again on demand if you want to. But if you do want to know more or get more information on this, please feel free to contact your local Schneider Electric representative, and they should be able to support you. I would like to take this opportunity to thank both our presenters today for the support on this topic. I think it's been a good discussion, and thanks to all who have been on this call as well for your time. Until next time, take care.